Now we're going to be talking about the first of the many groups, carbohydrates. Okay, so carbohydrates are generally polymers. They're polymers of a specific kind of monomer, and that monomer is known as a monosaccharide. Okay, now if that polymer has a length of up to 10 monosaccharide units, repeating, then it's known as an oligosaccharide, from the Greek word oligos, meaning few. Okay, and that can be a disaccharide, a trisaccharide, etc. I've written the word di, or rather the prefix di, in a different color because disaccharides are often not considered to be oligosaccharides. Some people sometimes break it up as monosaccharide, disaccharide, oligosaccharide, and then polysaccharide. So obviously it goes without saying that anything that has more than 10 such saccharide units is a polysaccharide. I mean, those are really long, often indefinitely long. And how are these interconvertible? Well, there are specific reactions, dehydration reactions, where you remove water molecules from between these saccharides and they link up together. This is nothing new. It's like when things esterify, for example, the same thing happens, right? An acid and an alcohol add up together, they lose a molecule of water and they form an ester. Similarly, two monosaccharides add up together, they form a disaccharide, and in doing so, they lose a molecule of water. So, by adding water molecules to polysaccharides, you can break them up into oligosaccharides. And by adding more water molecules to the oligosaccharides, you'll ultimately get back to these monosaccharides. Now, you might be wondering why these are called carbohydrates at all. And there's a reason for this name, and that's the fact that most monosaccharides, especially the early well-known ones like glucose, whose formula you must be familiar for a long time now, have this formula CnH2nOn. Okay, like C6H12O6. This fits that formula, and that is basically some Cn into H2O taken n times. So it was thought to be a hydrate of carbon. They thought that if you hydrate carbon, if you add water to carbon, you will get carbohydrates. That's wrong, and we know that today. And that's because there are some monosaccharides that are very similar to the other monosaccharides. They have very similar properties, but they do not follow the general formula. So now we understand what the actual definition of a monosaccharide is, and this definition will cover the exceptions as well. Actually, a monosaccharide is a polyhydroxycarbonyl or its derivative. So, if a molecule fits this condition of being a polyhydroxycarbonyl, okay, then any of these molecules plus derivatives of these molecules that haven't changed in structure too much will collectively be known as monosaccharides. So let's get to it. Let's see what these monosaccharides look like. Let's draw out a polyhydroxycarbonyl. So I hope you guys are able to parse what the term means. Carbonyl, let's start with that. What is a carbonyl? A carbonyl is a double bond O group. So it's an aldehyde or a ketone. Okay, let's see how we can fit that in. Let's take an aldehyde for now. Okay, 1, 2, 3, 4, 5, 6. 6 carbons. 6 carbons in this chain. So let's put an aldehyde group over here. Okay, so this is basically what? Hexanal so far. Right, so it fits the carbonyl definition. Now it needs to be polyhydroxy. So it needs to have OH groups on multiple OH groups. This would be a kind of monosaccharide, but often people will not call this a monosaccharide. They just go by the typical naming. They would just say it is a 2,4 dihydroxy hexanal. On the other hand, this is definitely a monosaccharide because there are many more OHs. The more the OHs, the better it exhibits more characteristic monosaccharide chemical behavior. So as you add more and more OHs, it becomes more and more like a monosaccharide. Okay. If I add a final OH such that every single carbon except the aldehyde carbon has an OH on it, then this is called a hexose. It's called a hexose. Okay. More specifically, since it's an aldehyde, I said it could be any carbon. Since this is an aldehyde, it's called an aldohexose. That's what it's called. If on the other hand, I were to do this, such that the carbonyl group is 3 groups in, then it would be a a 3 ketohexose, because it would be a ketone at the third group. Finally, if I were just to remove this like this, okay, remove one of the OH groups, effectively I'm removing the O, right, because the H remains to satisfy valency. Okay, so then this is a 1, 2, 3, 4. So this would be what is called a 4-deoxy 3-keto hexose. And here is our first example of something that doesn't satisfy this generic rule. Oops. Excuse me, that was a blunder. So the question then becomes that why is a generic rule valid? Well, if you think about it, let me put it back to the generic type. Each of these carbons has an OH and an H on it. So obviously most of these carbons will basically have, if this carbon has an OH and an H, this is basically H2O. One of these carbons will not have that, it will have just an O. Okay, that's the carbon bearing the carbonyl group. Or if it's at the end, it will have an O and an H. But at the same point in time, for the one that has just an O, there's going to, let's look at this. This carbon has just an O, it doesn't have an H at all. But this carbon has an OH as well as an H, and this carbon has an OH as well as an H. Okay, and by that I mean an H2 spare. This carbon has its own OH-H pair that will give it the H2O group, and it has an extra H. This also has an extra H. This carbon has no H's at all. So when you combine this and this with this, again you get another H2O. So effectively, if you have N carbons, you will get CnH2O N times. But then as you can see, this deoxy guy, if you just remove one alcoholic group, the reactivity won't change too much. It will still exhibit most of the reactions of monosaccharides, and so this is still called a monosaccharide, but you can see it is now different. It has lost one of the O's, so there will be one O less in this formula, and that's 4-deoxy 3-ketohexose as a result. Okay, so this is how we name monosaccharides, either aldohexose or whatever position, ketohexose, or not even a hexose at all. It can be a triose, tetrose, etc. We generally need it to be at least 3 carbons long, so we start from triose onwards. Okay, so that gives us a good definition of a monosaccharide. You can do some other kinds of derivatives. We'll come across them in a while, so I won't bother showing you examples right now. And now let's move on to studying the stereochemistry of these monosaccharides, because I'm sure any of you can spot a lot of chiral carbons over here. So let's move on to studying the stereochemistry. Right, so now we're going to be talking about stereochemistry in monosaccharides. The topic is stereochemistry, the Fischer projection and epimers. And really, these two concepts, the Fischer projection and epimers, can be subsumed under the larger topic of stereochemistry. Now, I hope you guys recognize this compound here drawn in pink. You can take a moment and try and identify which monosaccharide it is, and feel free to pause the video to do so. So I hope we've all come to the conclusion that this is definitely aldotriose. It is 3 carbons long. Each carbon has an OH except for the aldehydic carbon. So it's an aldose and it's a triose. Therefore it's an aldotriose. But you can see that these two aldotrioses are not identical. This has an OH on the wedge and an H on the line. This is an OH on the line and an H on the wedge. Right? So we can see clearly that these two are of opposite stereo configurations. Right? If one is S, the other will be R. You can work out which is which. Now, therefore there is one stereo center over here, right? There's just one stereo center. One stereo. So there's one stereo center in this entire structure. Now let's look at our familiar friend aldohexose, because that's the model we took last time, right? So when you look at aldohexose, this being an aldehydic carbon is clearly planar and therefore not chiral. This carbon has an OH, but it also has 2 H's, and therefore both these carbons are achiral. What remains, therefore, is the carbons in the center. Each of these carbons has 2 different lengths carbon chains on either side, an OH and an H. Okay, that makes this all four of these carbons very much chiral. And therefore aldohexose, whose formula by the way C6H12O6, has 2 to the power 4 stereoisomers. And more importantly, in general, we can say aldo-NOs is going to follow the formula 2 to the power n minus 2 in terms of its isomers, because we're going to rule out the aldehyde and the achiral primary alcohol. So this covers the basic understanding of stereochemistry, and we've got this neat formula that is applicable for aldose sugars. What about the Fischer projection? You ought to have covered the Fischer projection when you started out studying stereochemistry in the first place, but in case you haven't, I need a quick refresher. This is how it works. These are the two achiral ends we have. We're going from the highest priority carbon to the lowest priority carbon. And what we're going to do is we're going to draw these dashes. 1, 2, 3, 4. Each of these dashes represent the 4 different chiral carbons here. Now say I have this structure over here. This is a form of aldohexose. Very unimaginatively, it is named allose. As you can clearly see, all the OHs are on the same side and all the H's are on the same side. But what do these sides mean over here? What these sides mean is that if I look at this carbon, it's going to have these 4 bonds, the 2 vertical bonds and the 2 horizontal bonds. And they're going to be in some vague plane or other. But if I can rotate these bonds, and we will proceed to do this soon with an actual physical atomic model to understand this concept. If I proceed to rotate these bonds such that for this carbon, I'm talking only about this carbon right now. For this carbon, if I have If I look at this carbon and I rotate it in such a way that the CHO and the long carbon chain, which goes CHOH and then so on and so forth, both these vertical bonds are backwards from me. So you remember that this carbon is at the center of a tetrahedron, right? So we're orienting it so that 2 vertices are towards the viewer and 2 vertices are away from the viewer. Namely, the horizontal vertices, whatever is horizontal over here, the horizontal vertices are towards the viewer, the vertical vertices are away from the viewer, or rather the vertical bonds. So when we've done this, in that particular case only, when these are away and these are towards, the OH will be on the right and the H will be on the left. That is what this means. Right and this on the right and left are only in this particular configuration. Understand why. Imagine I flip this around. When I flip this around, if I just flip this structure around, then both the groups that were going away from you will now be coming towards you. Right? So these groups are towards you. And earlier the OH and H were towards you and now they've gone away from you. Right? But also when they've gone away, since you've rotated it like this, what was OH has come to this side and what was H has come to that side. So there's a complete swap here. And we get these bonds which are going back into the plane and have the H and the OH. So in this configuration, it's exactly the opposite of the Fischer projection. So the Fischer projection depiction is only valid in the previously drawn conformation where the vertical bonds are going into the plane, receding, and the horizontal bonds are coming out of the plane or approaching. In the opposite configuration, in the opposite conformation, the actual configuration will be exactly the opposite of the Fischer projection. So always remember to check that the vertical bonds are receding and the horizontal bonds approaching before you try and match it with this. If it's the other way around, you must match it with the opposite of this. I hope you can see this, and it's very clear. So that's the Fischer projection. Now let's look at something interesting. If I look at allose, now obviously I can put all these OHs onto this side and all the H's onto that side, and then I'll get the enantiomer of this. And if I just switch one or two of these stereocenters, I'll get diastereomers of this. This specific kind of diastereomer, say something like this. This is the kind of diastereomer where we've flipped only one of these configurations. The configuration at only one particular point. That is known as an epimer. Right? So these two, let me switch the color again. These two compounds are what are called C2 epimers. So an epimer is basically the opposite of an enantiomer. In an enantiomer, you flip all of them, and in an epimer, you flip only one. This pair are C2 epimers because they vary at the second carbon. The first carbon is aldehydic, and the second carbon, they have opposite configuration. This epimerization process is extremely important to talk about because it will be relevant to when we talk about how Fischer, the same Fischer who came up with this Fischer projection, led a study to find out what the structure of glucose and other monosaccharides actually looks like. And when we talk about that, we're going to need to understand what C2 epimers are. So now we're going to talk about this process that I said the epimers are highly relevant to, and that is the Kiliani-Fischer synthesis and the rough degradation. Okay, so it's possible to have a monosaccharide of some length n plus 2. So you can see you have CH2OH, then CHOOH repeating n times, and then your aldehyde. This is an aldose sugar. You mustn't think that all sugars are aldoses just because we're doing this with aldose examples so often. It's just that this particular, the sugars that we are most often interested in happen to be aldoses. When it undergoes the Kiliani-Fischer synthesis, what happens is this CHOH opens up into an n plus 1 CHOH. So this CHO becomes a CHOH, and a new a new aldehyde is added. Okay, this actually happens via addition of a cyanide group, and then we have to open up that cyanide group. It's a typical nucleophilic addition. It's not a very difficult reaction. It's just not in the syllabus, so I haven't given the mechanism. Similarly, you can do a step down reaction, which is called the rough degradation, in which this is oxidized and the aldehyde is removed, and therefore the remaining part, which is CHOH, this in turn gets oxidized to CHO, which is an aldehyde. So this is another possible reaction that takes place. And the reason I said epimers are relevant is because the CHOH can open up to the CHO can open up to be a CHOH with the OH either on the right or on the left. In the Fischer projection, the OH can be on either side. It can either be like this or it can be like this. So whichever way it opens up, you'll have both the C2 epimers. And similarly in the rough degradation, both the C2 epimers will convert into the same thing. So what Fischer did is he wanted to try and understand how all these aldoses are related to each other, and he performed some reactions by stepping up and stepping down to figure out the exact structure of glucose over here. So he would step it down and find out the structure of arabinose, step it down and find out the structure of erythrose, and this way he would figure it out. Now you might be wondering what this weird stick figure is. It's basically a very quick representation of the Fischer projection, in which this circle at the top represents the aldehyde, the CHO. Whichever side these branches are pointing to is whichever side the OH or the OH is on. So whichever side the OH is on is the side to which this white branch is pointing. Okay, and whichever side the H is on has not been shown. And at the very bottom, this arrow over here indicates this last CH to OH at the end of the chain. Is that clear? Okay, cool. So this is triose, specifically aldotriose. And this is the structure, aldehyde, one OH, and then another achiral OH. We perform the Kiliani-Fischer synthesis and we get both the C2 epimers, erythrose and threose. In the case of erythrose, these two OHs are erythro to one another, which is what we say when they're on the same side. In the case of threose, they are trio to one another, hence the name. So erythrose and threose. Now again, if I perform Kiliani-Fischer synthesis on erythrose, I will get ribose with 3 chiral carbons, all with the same configuration, and arabinose, which is the C2 epimer of ribose. And similarly, if I do with threose, I get xylose and lyxose. And finally, if I repeat the whole process another time, I get allose, altrose, glucose, which is the most interesting, mannose, gulose, indose, galactose, and talose. Now you might be wondering something. I hope you are at least. The last generation are the aldohexoses, right? Because there's one carbon here, 4 carbons in the middle. So aldohexose. For the aldohexose, the number of stereoisomers should be 2 to the power 6 minus 2, that's 2 to the power 4. 2 to the power 6 minus 2, which is 2 to the power 4. That should be 16. We have 1, 2, 3, 4, 5, 6, 7, 8. Where are the remaining 8? Pause the video and take the time to see which 8 stereoisomers we have missed out on. Okay, so what I hope you realized is that we started with this triose. We didn't start with this triose. What I began by saying last time is that triose itself has 2 stereoisomers because it has 1 stereocenter. This triose would have given us the remaining descendants. So it would have given us 4. So if we added this as well, we'd have 4 guys here, 8 guys here, and 16 guys here. Why don't we count these? Why aren't these considered separate molecules? The answer is because they're not really. Let's see what happens. Let's look at glucose over here. Let's just assume for a brief moment that we could just flip this last chiral carbon around in glucose. We would get something like this, right? This would be glucose flipped. But look carefully. Look at indose. This is indose. So the C5 epimer of glucose, where we just switch one stereocenter, is the enantiomer of this indose. Okay. So as a result of this, to nomenclate them very easily, this is known as D-triose. It's also called D-glyceraldehyde, but glyceraldehyde is just a fancy name for triose, and I want to use this O's nomenclature to be consistent. If you see the word glyceraldehyde, you should know it is referring to this. Okay, it's D-triose when this is on the right hand side. Anything derived from this via Kiliani-Fischer synthesis is prefixed to the letter D. D-erythrose, D-threose, D-ribose, etc. D-arabinose, D-xylose, you get the picture. This is also D-glucose. And this is D-indose. D-indose. Okay, that's D-indose. Now what we're saying is, when I take the C5 epimer of glucose, I get the opposite, and the C5 epimer is called L-indose. And this guy is known as L-triose. So anything derived from L-triose with the thing on the left, all these guys would have the last chiral carbon. The last chiral carbon would be on the left. Here every chiral carbon is varying except the last one, right? That's all on the right because it's from D-triose. So if I used L-triose, I'd get the ones on the left and I'd get L-indose. So the C5 epimer of D-glucose is actually L-indose, and therefore being an enantiomer, almost all its chemical properties are the same. Only when it reacts with another chiral compound or when we're talking about the specific rotation of light is there a difference between L-indose and D-indose. And that brings us to a conclusion on this topic about the stereoisomerism of aldoses. Okay, now we're going to move on to some specific reactions of monosaccharides. The first of those is addition with acetic anhydride. Okay, and this gives rise to a pentaacetate, a sort of ester, where all the 5 OHs, Fischer thought, ended up becoming esterified with the ACO. So his conclusion, Fischer's conclusion, was that there are 5 OH groups. Okay, which is not untrue. We have 6 carbons and then one of them has a double bond, so the remaining 5 have OH groups. Then he tried oxidizing it with weak reagents and he got what are known as aldonic acids. In the case of glucose, he got what is called gluconic acid. Let's see what happened over here. Basically, if you have CHO, yada yada yada, then that CHO over here opened up and became an HCOOH. So this sort of transformation occurred over here. This is oxidizing just the aldehydic group. It doesn't oxidize any of the OH groups on it. Okay. And what sort of weak reagents are these? Well, you should know the reagents very well. So let's write them down. Okay. These weak reagents, so this point is being explained over here. We have Tollens reagent, Benedict's reagent, Fehling's reagent, and finally we have bromine water. These are considered mild oxidizing agents. They will accomplish this. Next, we have reduction with HNO3. This gives an aldaric acid, which earlier used to be called a saccharic acid. Unlike an aldonic acid, where only the CHO is oxidized, here what happens is pretty cool actually. Excuse me. Even the primary alcohol at the opposite end of the chain gets oxidized to a carboxylic acid, and only the interior ones remain intact. This, I hope you are all aware, is tartaric acid. Okay, so you can see quite clearly how even tartaric acid is actually a kind of monosaccharide. It's just oxidized at both ends. And also you can see that this is meso. It carries a plane of symmetry. So what he did after he got this sort of result is that he would perform rough degradations, get them down to smaller and smaller samples, and keep checking if the precursors to the aldohexoses he was studying, did those precursors have a plane of symmetry or not, by constantly performing a rough degradation, cutting it down by one carbon and then adding HNO3. And by doing this, he was able to figure out what the possible structures of glucose might be, what might be the possible structures of gulose, indose, and he ruled out what all the other structures must be, and he honed in on the actual structure of glucose, which we just saw. Okay, so these are these three. Finally, reduction with hydrogen iodide gives you N-hexane. All this means is that glucose is based on a straight chain and not on a branched chain. So this was the other piece of information he got. It's a straight chain compound. With these pieces of information, Fischer's understanding of glucose was complete. He was able to ascribe it a structure. Of course, he did a lot of detective work in this step. I just briefly said he would perform a rough degradation, bring it down, oxidize it to an aldaric acid and check for planes of symmetry. That was a lot of experiments. It took him many days, many months, but ultimately he got to this structure of glucose. So now there are three more reactions that glucose carries out that were not part of Fischer's analysis, but we're going to go through them because they're important reactions that and each of them will take a certain amount of individual explanation. So let's move on. So the first reaction we're going to be talking about is base catalyzed isomerization. And what's happening here is that we have a glucose molecule, and in the presence of a base, it's undergoing keto-enol tautomerization. Okay, and it's forming this enolic structure over here. And then it re-undergoes keto-enol tautomerization, but this time, this OH ends up becoming the ketone, and that remains as the alcohol. Pretty neat, huh? So this keto-enol business allows you to convert glucose to this sugar, which is known as fructose. Many of you will know that fructose is the same molecular formula as glucose. This is borne out by the fact that all you've done is a form of isomerization. More importantly, this fructose can again undergo keto-enol tautomerization, but this time, since this has become achiral, when it re-undergoes keto-enol tautomerization, you will have this, but you will also have the other product. You will also have the product where these two are switched around, right? Now, why is this important? Why is it important to see that glucose, fructose, and what is the C2H of glucose? Mannose. Why is it important to see that glucose, fructose, and mannose are exchangeable? Because that means that though fructose is a 2-ketose, it exists in some form. Some of it, when you have a fructose solution, some of it will undergo keto-enol tautomerization twice and become glucose or mannose, which are definitely aldohexoses. So, if I look at Benedict's test or Fehling's test or for that matter Tollens test, because these three tests all occur in basic media, the Tollens has gone a bit let me write it again. Because all these three occur in basic media, some of the fructose via this will turn into glucose. This fructose, which has some part which is turned into glucose, will irreversibly turn into gluconic acid. Okay. Now there is some K1 value here, some K2 value here. These are equilibrium values. To maintain this K2 value, whenever this intermediate forms, more of it will turn into glucose than will turn back into fructose, because some of the glucose has disappeared. It's been consumed up, right? The glucose has been consumed up. It's turned into gluconic acid. This has gone and it has turned into gluconic acid. So it's turned into gluconic acid. So to maintain this K2 value, whenever this enolic intermediate forms, it will prefer to turn into the glucose than into fructose. Therefore, as the enolic intermediate decreases, fructose will keep turning into this intermediate. Ultimately, all of the fructose via this complicated chain will get converted into gluconic acid, and so you cannot use Benedict's test, Felling's test, and Tolling's test, which I usually use to distinguish between aldehyde and ketone, to distinguish between aldose and ketose sugar, because these OHs allow them to interchange the position of the aldehyde group and cause mayhem. And this is important, so it shows that fructose, glucose, and mannose are all interconvertible. This is the first of the second of those three reactions we're talking about, the formation of phenyl hydrazone and osazone. So the formation of phenyl hydrazone is something we're already familiar with. I've taken the example of glucose, but I've cut it off after the second carbon. Obviously, the structure continues, but only the first two carbons actually participate in the reaction, and so we're not going to draw out the whole structure every time. We add phenylhydrazine and we get phenylhydrazone. This is typical addition to aldehydes. However, there is then a rearrangement of sorts that doesn't take place in ordinary aldehydes. What is this rearrangement? The hydrogen on the second carbon migrates to open this double bond over here. So this double bond here, this hydrogen migrates to nitrogen and breaks open this double bond. But this carbon still doesn't get an additional hydrogen or any other kind of valency, and so the carbon shifts its double bond down here, and this carbon has lost the hydrogen, so it's happy to accept this double bond. Next, what happens is a second rearrangement takes place. This hydrogen over here, which is on the OH, that moves to this upper carbon. This gives you H2C, NH, NHPH, and this carbon has now become a ketone. Now again we add phenylhydrazine, and now we get this sort of structure. So there's a double bond here. This is a genuine phenylhydrazone, and over here we have this single bond and this long structure. But this actually is a very long and heavy thing, and it will try and tend to get back to a double bond over here. This rearrangement is actually one of those one of those intermediate states which aren't very stable. It's stabler to have the double bond with the nitrogen up here. So again, the upper nitrogen will try to regain its double bond, and to do so, it will do something really cool. It will get rid of one of these hydrogens, okay? And this hydrogen will come, and with this pH NH, it will go up as aniline, pH NH2. So now we're left with double bonds in both these places, but the lower one just has an NH. It doesn't have an NHPH. Now again we add phenylhydrazine, the third time in the reaction. And now we have the same molecular formula both above and below. Double bond N, NHPH, double bond N, NHPH. And here there is a byproduct of some ammonia. What is ozone formation useful for? Firstly, it can tell a particular sugar apart from its deoxy version. Okay? If instead of glucose, this was 2-deoxyglucose, then this would have been just hydrogen, not OH. Then it would have formed the phenylhydrazone, but the second and third steps wouldn't have taken place. Okay, so it can tell, let's write that somewhere, sugar versus 2-deoxy sugar. So it helps you tell the sugar apart from the 2-deoxy sugar. There's another conclusion you should understand from here. Okay, that conclusion is fructose and glucose, these two compounds have the same osazone. same Monosaccharides. So why is that the case? Because if this was fructose, then there would have been OH here and the double bond over down below. But it doesn't matter which one is above and which one is below. The same reaction would have taken place. The third point you should know, this does not carry on. If you add 5 equivalents of pH, NH and H2, it's not as if the third carbon is also going to get this. This is a very bulky group. At least here there will be internal hydrogen bonding between these two chains. And if you keep increasing it, that's not going to be the case. So it stops at the second carbon. It will not proceed for the third and fourth carbon if you keep adding pH, NH and H2. This is the last specific reaction we're going to study that has to do with glucose or aldohexose. That is the oxidation with HiO4. To be accurate, this is the last we're going to study with this particular structure, and we'll talk about a few alternative structures of glucose after this. So when we look at this particular compound over here, HiO4 is a powerful oxidizing agent that can oxidize two groups parallelly. So it will oxidize two side by side or two vicinal groups. This can work for an aldehyde and OH group. It can work for a carboxylic acid and OH group, carboxylic acid and aldehyde. The only stipulation is if you have two OH groups, they must be facing in the same direction like this, not like these. Okay. What we're going to do is we're just going to see what happens in an excess of HiO4. How does this get oxidized? So let's see how that happens. We're using an excess of HiO4, remember. So let's look here at the bottom. Oh, by the way, one thing I should have mentioned, when HiO4 oxidizes, it always cleaves the carbon-carbon bond. So it will cleave this bottom bond, CH2OH, this is an alcohol, it will become an aldehyde. So we have CH2O, formaldehyde, okay? And this guy will become an aldehyde too, because this is also an alcohol. So there will be an aldehyde here. So we had, this has become an aldehyde being the lowest, then this has remained the same, this has remained the same, but this will not remain the same because this bond will also be cleaved. So we'll have a dialdehyde structure, and this guy, which was an aldehyde previously and has been cleaved off, will become formic acid, HCOOH, and this dialdehyde. But remember, we have an excess, so it will react again. This time, both of these, upper and lower, will go off and become carboxylic acid. So we have two more formic acids forming, and whatever is in the center will become a vicinal dialdehyde. Earlier, since these were both in opposite directions, they couldn't have been degraded directly. Now we can degrade them as directly as we like because the two of them are matching the same direction. So we will, when we break this bond, again these are both aldehydes, we'll get two more formic acids. So the final answer is if you have HiO4 and you oxidize glucose, you will get 2 plus 2 plus 1, that's 5 formic acids and 1 formaldehyde. This can be given to you with any random carbon chain. The same thing, you just keep slicing it from, you can work your way in from the ends. Generally, you'll get the same product whichever way you work at it. Slice every bond and oxidize whatever's on either side, and you'll get this. You'll get these answers. How many formaldehydes and how many formic acids? This can be given to you with any sugar whatsoever. I've just given the example with glucose.